Yeah, so the uranium, thorium, lead system incorporates the three elements, uranium, thorium, and lead. So uranium and thorium, both elements decay and form a common lead element. And during fractionation or during partial melting or fractional crystallization, any of those two processes, because those are the main two processes happening in the Earth's interior, uranium and thorium are incompatible, right? So they prefer the liquid phase. They prefer the liquid phase, and they automatically incorporate. I mean, the majority of the budget of uranium and thorium are incorporated in the melt. So in igneous rocks, probably the compositions like granitic, for example, uranium and thorium are enriched compared to basalts or ultramafic rocks because they are more mafic. Therefore, the incompatibility of uranium and thorium prefers partitioning much more than for the mafic rocks. So felsic rocks contain a lot of uranium and thorium. So therefore, the crust or the continental crust, which is a product of melt, right, should contain a lot of uranium and thorium. And as a result, you should expect with time, the crust must have evolved to high lead bearing compositions than the mafic other earth reservoirs. Okay, so the mantle should be depleted because it is mostly the residue. So uranium and thorium is not much enriched in the mantle, but in the crust you have a lot of uranium and thorium. So that means parent isotopes are there. That causes a lot of daughter isotopes to be enriched in the crustal products. So this is important, and you can see here the upper crust and lower crust, the compositions of uranium and thorium, right? This is elemental uranium and thorium. Okay, so this is the composition, and you can see how the mantle contains those. See, it's 0.05, but the crust contains 0.6, 10 times greater than that, and thorium much more than that, right? So therefore, you can see the crustal values are higher when compared to the mantle values. And also, if you consider the uranium and lead ratio, so since uranium is enriched in the crust, it should give relatively lower ratios, uranium and lead ratios, right? So that's why here you see just 0.1 in the lower crust and 0.18 in the upper crust, but in the mantle it's 0.14, still like intermediate to these two. It's because although uranium is more incompatible, lead is not that incompatible compared to the crust when you consider crustal and mantle values. So you can see here their difference, distribution difference. When the mantle is 10 times lower in uranium, you can see the mantle contains a little more lead than the ratio that can contain with respect to the uranium and thorium, right? So although this is a low number, but it's a bigger number, right? 10 times bigger than the normal uranium value, right? So therefore, this ratio is affected due to that, but still the average crustal values, if you see the average crustal value here, this is the crustal value average. If you take the average crustal value, still because the upper crust is the mass of the upper crust is also high, so therefore little greater than the mantle value you can expect for the uranium lead ratio also, right? But the elemental values clearly high in the continental rocks. And also you can compare upper crust and lower crust together, because lower crust is mafic compared to the upper crust, right? Upper crust is heavily acidic, but lower crust is less acidic, right? Uh, it's mafic, but not as mafic as mantle, right? So that is also there, right? So you just think that lower crust is intermediate to upper crust and mantle in composition wise. So therefore, this type of variation you can expect in these reservoirs, right? Okay, and as we said before, uranium decays to lead, right? So normally, what decays forming lead is uranium, these isotopes, okay? Because naturally occurring uranium contains two radiogenic isotopes. So these are the two radiogenic isotopes for uranium. And if you consider thorium, it exists primarily one radiogenic isotope, that is 232 thorium. Okay, so in this situation, you can expect uranium 38 decays, uranium 35 decays, and thorium 232 decays. So therefore, you must expect three decay schemes for this system, as this system producing lead isotopes. Okay, so radioactive daughters produced are lead isotopes. Okay, by 238 uranium, 235 uranium, and 232 thorium. So these are the decay mechanisms, decay parental isotopes of uranium lead and thorium lead system. If you don't hear, please let me know, right? If any interruption is there, please let me know. And also please input your registration numbers into the chat box. Okay. And these are the decay schemes. You can see the three isotopes, 238, 238. Here you have 238, and then 235, and thorium 232. They decays to lead 206, 207, and 208. These are the three isotopes produced by uranium thorium decay system. In both cases, in the three cases, uh, what you get is helium released, helium 4. Helium 4 is released, and some beta particles remain, and some energy is dispersed, right? So the specific lead isotope formed in these three schemes are like this. That means 238 corresponds forming 206, 235, 207, 232 thorium, 208 lead, right? So these are the three decay systems. You have to remember these three decay schemes of lead isotopes, right? So this mechanism is important in the because when you deal with some equations in the future, that will be useful. As we did for strontium and neodymium, we have to do the same type of referencing or standardizing, or in other words, normalizing, right? For a stable isotope, right? Do you remember 143 neodymium was divided by 144 neodymium, right? Strontium was divided by 86 strontium, remember? So like that, you have to reference, or you have to standardize, or in other words, you have to normalize these lead isotope ratios for a stable lead isotope. So the stable lead isotope variety available is 204, 204 lead, right? 204. Here we have 206, 207, and 208. 204 is stable, which is not radiogenic. So therefore, we can use that non-radiogenic isotope for referencing purpose. And we can construct the similar decay equations like in the previous systematics for strontium neodymium like. The same way you can construct some decay equations, and in this situation the important feature is you are getting three independent ages, right? You are getting three independent ages for this isotopic systematics from a single sample, single analysis. That is the advantage. For example, here you have one age from this systematic, and another age from this systematic, and another age from this systematic, right? So even one sample, you can get three ages. So this is very, very convenient because you can compare those three ages. So if they are very close by, then you are very much confident that real age of this rock is this much, right? Because you are testing with three systems like, but actually you are doing only one analysis, but you are getting three ages. So that is an advantage in the lead isotope system, which was not available in strontium or neodymium systematics. So in this case, you can verify your age of the rock uh, because you are getting three different or three independent ages, right? They are mutually non-dependent. So therefore, you can compare them and verify the preciseness of those ages. So that is very good, right? So like we had for the strontium, rubidium strontium. So you can remember the age equation. Strontium 87, 86 equals initial strontium plus the radiogenic product. This is the radiogenic product, okay, at a t time interval, right, for a time span of t. We get this much of radiogenic product. So therefore, the measured today, present day measured isotope composition equals initial amount plus the radiogenic product, right? This is the initial amount, and this is a radiogenic product over t years, right? So similarly, you can construct equations for uranium lead systems. So here you have 238 system. 238 produces 206. So therefore, 206 divided by 204. 204 is the reference isotope that we use to normalize, right? So measured composition should be equal to initial lead 206 isotope composition plus the radiogenic product. So this is the radiogenic product of 238 decay. So this decay produces this much of radiogenic amount, right? So plus initial amount equals the present day measured value. What was available first plus the radiogenic product over the interested period should be equal to whatever the number that you found by your measurements of these isotopic systematics, right? So similarly, you can have 235 system also, that which produces 207. So 207 measured equals 207 initial plus radiogenic product, right? So these are the two uranium system. And for thorium, 232 thorium, which produces 208 lead. So therefore, measured lead isotope composition equals initial 208 lead isotope composition plus the radiogenic product, the radiogenic decay product. So lambda 1, lambda 2, and lambda 3 are corresponding decay constants for these three systems. I think it's not very difficult to understand, right? So the same equation, but only the difference is you are applying the lead isotopes here, right? So you always remember 238 corresponds to 206, 235 corresponds to 207, and 232 corresponds to 208. So this is very important, right? So you can't interchange these ones, and don't get confused also. Remember the correct system and apply the correct terms there in the equation. Right. Some accepted values are there. That means the decay constants, for example, for 238 to 206, decay constant is this much. Right. This is the decay constant. And for the second system, 207, you have the decay constant, this one, and you have here uh, another decay constant for the thorium system, right? And also uh, for many samples or many material, many terrestrial materials, this ratio is a constant, right? It is I mean, I'm not going to explain as to why it is constant, because it is, we need to consider some complex processes, but just for the time being, you remember that 238 divided by 235 uranium in a material, any material, in any natural material, is this amount, this much. The ratio is coming up as 137.88. So this is a very, very important observation. And IUGS has stipulated these values. They have a subcommission on geochronology, and they have stipulated these values as accepted values, right? So decay constants, and this is the ratio, uranium 238 to 235 ratio, right? So you have some other values also here, just for your reference. You can compare the half-life. You can compare the half-life here, and check respective half-life. So this is the uranium system 238, 232, and 235, right? So these are the three systems you have, and you have the half-lives. Okay, so these are the half-lives. Yeah, and the largest decay constant is given by which one? Yeah, you just compare these three, right? This is the 10 to the minus 11, so that should be more smaller, isn't it? So this is 10 to the minus 10, and this is bigger, and this is smaller, right? So this is the smallest one. So 207 is the largest, isn't it? Okay. Right, so these are some accepted values. See, yesterday we talked about the CHER, quadratic uniform reservoir. It's a neodymium isotopic composition to the 2466 decimal point is given, because this is very, very important number, right? Normally, neodymium isotopes, I told you, we are dealing with the decimal points, at least 4 decimal points, but the six decimal point is the best best to use, because they are changing very slightly. Very small numbers are changing, only the last decimal points are changing. Therefore, for many materials, natural materials, you get initial 512 as common. Okay, so therefore it's better, rather than rounding off it to the fourth decimal point, consider the next 3 points as well, right, for more precise calculation. That's why actually we consider the epsilon notation also by multiplying 10 to the power 4, so that you get you end up with some meaningful numbers, rather than dealing with the decimal points. So when we apply the uranium thorium lead system to rocks or to natural materials, it's very important that we get correct ages, right? We get correct ages. Of course, it's important for any isotope system, but for uranium lead system, it's important because you are having three isotopic systematics at one time, right? When you deal with these isotopes, so it will reflect the preciseness. So we call, if the three isotopic systems, the uranium 235, 238, and thorium 232, these three systems, if you are getting a very close or very similar date or age, we call the system is concordant, right? We call it the system is concordant. But if they are different from each other considerably, then we call it discordant, right? So we will consider those two scenarios later. But just remember, if you are getting three dates or three age data similarly, then you can consider it as concordant, right? So that means the same age. But if they are different, then you can call it discordant. Okay, so we'll see why we use these two terms and at what kind of situations we can use this, right? So to give you a concordant age, whatever the material or the mineral that you are measuring or considering, or even the whole rock, right, it should be remained closed for uranium, thorium, and lead throughout the history. Throughout its history, there shouldn't have been any exchange of uranium, thorium, and lead in the system. So that is one assumption. And we have used a correct initial lead isotope ratio. So that is also important, right? Initial lead isotope ratios we have to use correctly so that we can come up, we can solve the T term in the equation, because you have initial composition unknown and T time is unknown, right? So that's why we draw a line and made some estimations previously. Remember strontium and neodymium cases, right? And also the decay constants that we use are correct, right? They should be accurate. These are experimentally determined, and now the IUGS subcommission has stipulated these values as I showed you before, and these correct values are properly used. If then you get these concordant ages. Otherwise, you might get some discordant ages. And the uranium has not been disturbed, or thorium has not been disturbed. For example, if the processes like metasomatism occurs in the rock, or in other words, like some melt rock reactions happen during the history of the throughout the history of the rock that you are considering, then it will be a problem, right? So you must have uh, the system closed anyway for this isotopic systematics, so that you get a proper or clear age, right? And of course, the analytical results are correct, okay, and free of some errors, some human errors or some systematic errors uh, during the procedure, during the process. Uh, so all these conditions, if all these conditions are met, then you can believe the age that you get is concordant, right? And also you can see they are very close to each other. And as I said, the discordant means when you are getting the three different ages, at least two different ages, right? So in that case, you can say that the ages are discordant, right? So this can be due to some kind of breaking of our assumptions that we mentioned before, right? At least one or uh, few assumptions could have been broken during this process, right? So this can be like lead, uranium, or thorium loss. There can be opportunities for these elements to be lost from the system, because these elements are highly volatile compared to other elements like strontium, neodymium like elements. They are not non-volatile, but these are volatile. That means heating, upon heating, these elements can easily be uh, decayed, or not decayed actually, transferred to other types of elements. Okay, or otherwise they can be lost from the system, right? This is also possible. That means they are migrated from another to from the phase that we consider to another phase. So that means the equation is broken. The equation is broken. And also some product loss or even parent loss can cause discordant edges. So we call some situations lead loss. Lead loss means the produced radiogenic lead may have lost from the system. Okay, because I said they are highly volatile, so therefore this volatility may cause some problem with these elements. Okay, like lead. So uh, if you are getting discordant edges from a given analysis, probably you can use 207 ratio as the closest value for the real age, because you saw that the decay constant is largest in 207. So therefore it can give you a better age to the real value. Uh, so in case if you have experienced any trouble uh, like discordant edges in when you plot them, right? We will see how we can plot them later. Uh, then you can consider uh, 207H. Okay, 207H you can consider. And also one of other important matter regarding 207 lead is it's insensitive to recent lead loss. That means even the lead was lost due to some process. For example, metamorphism is a process that can cause some leaking of lead to outside environment, right? Or other words, there can be some kind of magmatic intrusion into the rock that you are considering. That can cause also disturbance to the lead budget, right? But if this disturbance has happened very recently, less than 500 million years ago, right? Recently means that, right? Less than 500 million in general, right? There may not be big contrast in lead loss because this 207 cannot show large discrepancy for a short period of time, right? Because it needs a longer period of time to give very contrasting isotope values. So this thing you might not understand clearly, but for the time being, you just think that 207 207 206 ratio is not affected much by the recent lead loss. Okay, if the metamorphism happened in maybe 200 million years ago, then still you get the correct age, although the system may have suffered some lead loss in it. But if you try to interpret 207, 206, or 208 ages, right? Ages derived from 206 or 207 age equations, right? For example, these ones, right? 207 doesn't affect much this one, right? But these ones, 206 or 208, may have been affected by the even a recent lead loss, right? So for that, actually, this lambda matters. uh, you observe that the lambda of 207 is the largest, right? So therefore it does not affect much on this recent lead loss. Okay, so there is something like that to consider, so you just keep that in mind. Okay. Okay, so we can see the relationship among these species, and we can combine these decay equations, because actually for our convenience we do this, right? Nothing for any scientific merit, but yeah, there is some scientific merit also, actually, but not too for a not for a too technical thing. That's what I wanted to mention, right? So we'll see how you can combine these two. You remember the two equations we had? These, not two, three equations we have, but we'll take these two first. you have 206, 204 equals 206, 204 initial plus 238 to 208 E lambda 1 T minus 1. Likewise, right? 207 also you have the equation. So these two equations, you can do some subtraction or division or whatever, like I mean, any operation, algebraic operation like this, right? You can divide these two, right? Or you can just subtract one from the other, right? Just to make some changes, right? Let's see what we can do with that. Okay, so here you can see 207, 204. The equation. First, what you do is you take this term 207, let's say this one, you take this term this side to the left side. So then 207, 204 measured minus 207 lead, 204 lead equals 235 to 204 E lambda T2 T minus 1, right? So that is there. So same thing can be done to the other equation also. And then you divide those two equations one by one. Okay, so this is one equation and this is another equation, right? So these two are divided, these two equations are divided, and then what you get here is you 235, 238, because you see 207 and 206 is there. Okay, I think you can understand what is coming there, because 238 is here, 235 is here. Okay, so this is similar term, so it cancels out. These are similar term, it's just a number, right? So when you solve it algebraically, initially you will end up with something like this. Okay, so the two equations, you have one equation here and the other equation is here. These two are divided each other, right? So you are getting something like this. And then you can you can see this contains this ratio 235 to 238. Do you remember the number or the value 235 to 238? See here, 235 to 238 should be what? You have 238 to 235, right? 238 to 235 is 137 0.88, 238 to 235. So let's see, 238 to 235. So you have 238 to 235 there as 137.88. But now what you have is 235 to 238. So that means 1 over 138, 137.88. Okay, it's a constant. So you can directly apply that number here. You can directly apply this here so that it becomes a constant, right? So no longer you need to measure anything related to 235 or 238, right? You don't need to measure anything related to that, because you can, you know, it's a constant. Even though you measured, you get the same constant. So therefore you don't need to measure. And you can consider this one. That means this term, right? What is this term? 230, sorry, 207, 204 measured, right? There is no m here, but this is the present day measured value minus the same of initial value. So what is this? The measured minus initial means what? Can anybody tell me? Measured minus initial. Measured equals initial plus radiogenic product. Measured equals initial plus radiogenic product. Okay, these two. Measured equals initial, this one, plus radiogenic products. Now what I am asking is measured minus initial. Measured minus initial means this has been taken to this side. So which is equal to the radiogenic product, the radiogenic amount. Okay, right. So here the measured minus radiogenic amount of 207, and here measured minus radiogenic amount, sorry, measured minus initial amount for 206. So that means radiogenic product of 237 is here, radiogenic product of 206 is here, right? So you can cut short this amount, writing in one way, another one way. That means you can write it as two. What we are getting is radiogenic amount of 207. Radiogenic amount of 207, right? 207 in the in here, right? Divided by radiogenic amount of 206, isn't it? Do you understand? 206. Why? Because you are getting the radiogenic production only from this equation. Okay, so you have radiogenic production of 207 by this term and radiogenic production of 206 by this term. So in isotope geology, what we do is to denote the radiogenic amount, we put a star here. Okay, we put a star here. So radiogenic product of 207. So if you see anything bracketed with a star, it indicates the radiogenic production, right? For 206 also, the radiogenic product of 206 also, to indicate, you can use a star. So what you initially get is the ratio of the two isotopes radiogenically produced. So which can all together be produced, represented like this, right? 207 divided by 206, but we are considering the radiogenic amount. So you can denote it in a way like this. So instead of writing all these terms, instead of writing all these terms here, you can replace it with this one, right? Because we are denoting the radiogenic product, a radiogenic amount. Okay, so star indicates the radiogenic amount, right? So you can use this 207 to 206 star instead of this whole term. So what happens if you write that? You get something like that, right? So this 207, 206 radiogenic amount equals this value. Okay, this value, right? So you have here it, you have written it here. So this is equal to this one, which is equal to this term. Okay, so this is just converting your equation into another form. That's it. Nothing. We didn't do any exchanges or anything, any operation we haven't done. Okay, just a matter of presentation only, right? The way you present the equation, just for our convenience. We'll see why we wanted to do that, right? So actually what we did was we calculated, or we denoted this radiogenic amount by subtracting the initial amount. That's what we did, because this is the initial amount. You have the initial amount here that was subtracted from the measured value. Measured value is here, right? This is how you get the radiogenic amount. So this is very simple thing, but just change the way of presenting the parameters of this equation, right? So is it clear? If anything is unclear, please let me know. Okay, right. So we'll see the same thing again. So we use the previous notation, the way, and we write down the radiogenic amount of 207 to 206, right? The same thing, which should be equal to this. Instead of this value, we can put 1 over 137.88, and then you can put this term there. So you are getting this equation from that, right? So this is more simplified than the previous one. So just for our our convenience, we can use this equation in this uranium lead systematic. So here you can see two systematics are combined together, 207 and 206, right? Two systematics are used here. So in this equation, no other terms involving uranium or lead or anything, right? I mean, 207 is there, 206 is there as lead isotopes, but no other terms. And also you don't have any uranium term there. Other terms are lambda T. So those are the things. So this is a very simple equation now. And what we need just is the isotope ratios of 207 and 206 to determine this TH, right? This HT can be determined if you know the isotope ratios of 207 and 206. So this is very, very convenient and very useful, because in our previous cases, we wanted to have other, even the samarium neodymium ratio also. Remember, we needed to know that to come up with the T, right? In the case of strontium isotopes, we wanted to know rubidium strontium ratios, okay, uh, to determine the T. But in this case, since this part is a constant, right, uh, we can just we don't need actually other terms other than measuring 207 and 206. So that's enough. So we can date the rock just by measuring 207 and 206, because lambda 1, lambda 2 we know, only unknown is T, right? But uh, in this equation, although it's simple, we have a little problem because we cannot solve this algebraically. Why? Because this is a radiogenic product which we don't know uh, the amount, although we can measure some isotopes, right? Once you measure, then you can do that, right? That's fine, but it's not simple equation. I mean, simply solvable equation. It's not simply solvable equation, because you have two unknown terms there. So you need extra equation to solve this one if you want to solve. But to avoid that, what we can do is, you can go for a tabulated format and make a diagram. So make a diagram means you can plot this star value in one axis, and uh, this value can be taken into x-axis, right? So there is I mean, if you can put this one and this one into the two axis, it should be able you should be able to find out an extra equation by like for example, if this is linear, actually this is not linear, right? This is not linear, but if it is linear, just for an example, you can plot some two values, just arbitrary values. You can put 0 here, and you can put corresponding t value there and plot here, and you can put 1 here and corresponding t value here, and plot the second point. Likewise, you can plot and draw the curve. After that, by the curve, you can get the for example, the gradient and intercept or something, and then you should be able to solve this. But actually, this is not y equals mx plus c type equation. This is a parabolic type equation. So, but still, if you are going for a plot, then you can solve this equation without an additional algebraic equation, right? So this is what we apply in mathematics. We are going for a graphical solution once whenever we don't know some of the parameters involved, right? So similar approach can be taken for this also, which will be very convenient for us to uh, determination of ages. So I will show how we can do that, because however much I explained, you don't understand, you might not be understanding how we can do that. But let's see. We will take uh, uh, different values for 207, 206 ratios, arbitrary values, any values. We'll take from 0 to some other some values, or even some decimals to some other numbers, right? In a table, first we put in we make a table with these values, right? 207, 206, and then you can have the corresponding this value, right? Because this is known, lambda 2, lambda 1 is known, t is unknown, right? But for different values, if you just put say 0 or 1 over here, then you can calculate t here, corresponding t here, because once you apply some number here, you are remaining with one unknown only, right? For the time being, you have two unknowns, but you make it an arbitrary value, you put into one unknown, and you can calculate the corresponding other unknown value, right? So likewise, you can have a table. So I will show you how you can do that. So different values of t can be found for different values of 207, 206. So that means we have two values now, sets of values, two sets of values for two axes to plot. So then you can plot whatever the curve you are getting there, and then from the curve you can find out gradient or whatever other uh, other parameters which is explained by the equation of that curve, and uh, find out the two unknown terms, right? This is like in the case of mx plus c, what we do is we plot first, and then what we do is we take m, right? We take m, and you can equalize this m into m for something like t involved uh, uh, term, right? Remember lambda t minus 1 for the age equation. So this m was equalized to lambda t plus 1. So from that you calculated t, right? From the c intercept here, you equalize it to the initial ratio, then you directly get the initial ratio. Likewise, we should be able to do some calculation there. So we'll see how we do it practically. See here. So different values of 207, 206, arbitrary values. You can take any value. Okay. For this, you put some numbers there, and then you calculate e lambda 1 t minus 1, right? Uh, for different values of t also we choose here. See, this is the t, this is the t, this is giga and billion, ga, right? Yes, to 10 into the power 9 means giga, giga nms, right? So zero point 0.2 giga nm, you put just 0.2 giga nm into this t, and get this number, and you put the same t value, and you get the uh, second parameter. So here you get this one, you get this one, and also you have sets of values for this one. So then you can construct the curve. This is what we go for a since we don't have other equation, we go for a graphical solution. So this is what we do in lead isotope systematics, right? So different values of T, we choose different values of these lead ratios, and then we calculate the other terms involved there. Okay, so we know delta, lambda 1, lambda 2, everything we know, and you can just apply those values one by one to this equation. Okay, for this equation you apply these values one by one, right? And then you can come up with uh, a new way of representation, right? New way of representation of this graph. But before that, you have to go back to the equation. You have to go back to the original H equation of this lead isotopes also, right? Let's see. Going back to the equation here, right? So this is just the reference value, right? Reference, I mean the normalized value 204. Remember, so you can just forget that one. You just forget that one and see like this 206 206 lead is equal, I mean measured, 206 lead measured equals what, 206, it's difficult for me to write. 206 lead initial amount of 206 plus plus what you have, this term means radiogenic decay, that means 238 uranium E lambda T minus 1. Okay, right, now you have this one, so you can make you can take this term to the other side. Just a minute, you can take this term to other side, that means here, then what you get is 206 measured minus 206 initial. So what does it mean? 206, what is it? 206 radiogenic amount, 206 star. Okay, 206 star measured minus initial means 206 star, right? So 206 star equals 206 star equals the remaining term, 238 uranium into E lambda T minus 1. So if you take this 238 into the left side, it means you divide it by 238 uranium, right? This is just grade 10 maths. 238 uranium, 206 radiogenic product divided by 238, because you just take it to the left hand side from the equation, equals E lambda T minus 1. Okay, so instead of this E lambda T, what you can do is you can replace E lambda T, this term, E lambda T minus 1 by 206 star divided by 238 uranium. Okay, 206 star divided by 238 uranium. Okay, so you can do that here. See, 206 star divided by 238 means E lambda T minus 1. Okay, similarly you can do for the other equation also, 207 lead star divided by 235 equals E lambda 2 T minus 1. All right, so so you can directly put these two values in your equation in these two places, right? Sorry, this is down, right? This is here and this one here. Okay, so instead of these two, you can put uh, these values if you want, right? Because we made it equivalent, right? We made it equivalent. Right now, you see what is happening there, right? So you draw the what the figure here, the graph here, and you take one as this axis and the other one as this 235, because we have 238, 235, right? So you make a graph using these two terms. You make a graph using these two terms, these two terms, xy, as x and y. You plot them, right? You plot them there, and you will end up with, for different values of these values, because you have this value, you have this value. It's like x and y. This is x and this is y, like, okay. So instead of x and y, uh, you have this one, x and y, right? So you can just replace those x and y by these two terms. That is what we have done here, right? So this is x and this is y. So you have the table now already. You have these all values, right? You have all these values starting from 0.2 gigaNMs to 1.6. So like actually you can start from the history of the Earth. So like 4.5 billion. You can start with this one, this number, and come down. Or you can just increase up to 4.5. Yeah, we'll take like that. We'll increase it to 4.56 billion years, right? And you can start from 0, present day, today, 0. Okay, so you will get these numbers, these values, by putting this t value and uh, uh, just by dividing these two, x and y, you get this 207 207 to 206 ratio value here, because you have already t value here, like that, and you can what you can substitute those t value here, and you get some number for this radiogenic value, right? So you have radiogenic value here calculated by using these x and y terms, right? You understand? If you put 0, everything becomes 0, right? Everything becomes 0, then this is also 0, right? And then what you can put, you put point 2, you put point 2 here, and you have point 2 here also. Then you calculate this much and you multiply it by 1 over 137.88, and then you get a number that is equal to this radiogenic product. So this radiogenic product is here, right? You put that number here, right? So for arbitrary values, you get arbitrary results also, right? Arbitrary values, here you put the arbitrary values from 0 to 4.5 billion years. Then you get some expected radiogenic values here also, right? And these two terms we represented in another term, that is star notation, that is radiogenic product notation. And we constructed this diagram. So when you start from 0, 0 is here, 0 value is here, and then you keep on increasing up to the age of the Earth, 4.56 billion years, up to here. Okay, so you have some values, so it's just a matter of plotting, right? In the previous case, you just plot here, right? You will get some values for different t's starting from 0 to 4.5 billion or 4.6, right? You get some radiogenic amount, some value, right? You can fill this table and you can use those values for x and y. So you have x here, you have x y here, like this. You have the couple, so you plot them. When you plot, you will get a curve like this. You will get a curve like this. So each point from this, for example, this is point 2 GA, this is point 2 GA. So maybe your point 2 GA is somewhere here. Okay, your point 2 GA represents these two values, right? So these two values you have for this point 2 GA. So likewise, you have all these points plotted on the curve. So that will produce a different curve like this, and which is called Concordia diagram. Okay, this is called Concordia diagram. So radiogenic products of this 206 and 207 are used to construct a Concordia diagram. Actually, this Concordia diagram we constructed without measuring anything, right? We did not measure any sample value, but what we did was we took this equation, and for this equation we replaced different values of t, right? Different values of t starting from 0 to 4.56. Okay, and then you found this term and this term, right? That's it, right? We didn't want to even utilize this term in the Concordia diagram, but we used x and y, these two terms, right? So you just plotted that Concordia diagram, and you can mark each point. For example, we marked here point. You can mark here point 2, because this is the point corresponding to point 2. Likewise, you can mark for GA here, the point corresponding to 4, point corresponding to 2. Then what we do is we take this as a reference diagram, because this is uh, universal diagram, because we did not use any sample for constructing this diagram. So therefore, but we use the theory which was applied for the uranium lead systematics. So this should be applicable for any natural sample, any natural material. So what now we do is we measure our isotope ratios by mass spectrometry, and we find out what is x and what is y. Actually, what is x and what is y means e lambda 2 t minus 1 and e lambda 1 to t minus 1. These two ratios, or in other words, we measure these isotopic ratios. These particular isotopic ratios we measure by mass spectrometry in uranium lead isotope system. So these two corresponds to x and y in this diagram, right? So once you get the ratio from the mass spectrometer, you know the x and y, then you can plot your sample here, right? One sample may be plotting here, and another sample may be plotting there, another sample may be plotting there, another sample may be plotting there. Some samples may be plotting outside like this, right? So likewise, you can just plot and see. If one of your samples plotted here, right, exactly here, then you can say that your sample is 2GA all, because this is the point which is corresponding to 2GA. Right? So your sample also plotted very close to that 2GA point of this curve. So then, because this is a reference diagram, then you can just compare it with the corresponding age and tell that this is the age of our sample. So this is the technique we use in uranium lead Concordia diagram in this method. Okay, so this is a reference diagram we construct, right? So your sample may correspond to different points like here, right? They are sometimes very close on this curve, or very close to this curve, some of the points, but some points might be going out of this curve also, right? So why you are getting very close to this curve or on the curve, it is just because when your age data become concordant. Okay, so do you remember concordant? What is concordant? Your age data, if your all the age data are three system, uranium, thorium, lead system, at least in this case, two systems, 238 and 235. If they are giving almost the same age, then they should be concordant. So such samples will plot exactly on the Concordia diagram or Concordia curve, this one, or very close to that, like this, right? Some of the samples may be plotting considerably outside the Concordia diagram. So such points we call discordant point. So we have concordant points and discordant point in our Concordia diagram. So concordant points can directly give you the age of the rock that you are considering, right? If it is plotted on the curve or very close to the curve, right? Very close to the curve means it is determined by the uncertainty, plus or minus value, right? This is determined by this the software that we are using for this Concordia diagram, right? You can do this manually also. You can construct the Concordia. Actually, if you plot this Concordia diagram in a graph sheet, and you get these ratios from mass spectrometry, you can manually plot. You can manually plot and see whether it is concordant or discordant, right? If it is concordant, then you can give a date also. But calculating the error, uncertainty may be very difficult in manual methods. So what we do is we use some Excel-based programs or some softwares which incorporate this Concordia diagram and some programs. What do you call it? Some algorithms which determines the age based on this theory. Okay, so in a Concordia diagram, what we get is 206 to 238 ratio and 207 to 235 ratio. So in uranium lead dating system, these are the two ratios we have to consider in isotope measurements, right? We don't need the previous ratios that define this isotopic systematic, like these ones, right? You don't need to measure it. Of course, by mass spectrometry, they are also measured automatically, but you don't need to consider them. But you need to consider these ratios only to construct the Concordia diagram, right? In uranium lead isotope systems. Okay, so this is the Concordia diagram, which is used to determine the age of a rock. So graphically, we can find out. Sometimes you have some clusters like this from your samples, right? So that indicates your samples have formed in a range of ages. Continuously some time span. Some maybe from 50 million years to 100 million years, there has been magmatism or something, right? That indicates, right? So this is very convenient way of determining the ages of uranium lead system. And these samples which are plotting outside the Concordia, we call them discordant. So this discordance can happen due to several reasons. Discordance can happen due to several reasons. Actually, the main assumption that we have during this isotope systematics is this should have been a closed system, right? So I think we discussed about the discordant ages, right? The reasons for discordant ages: uranium, lead, or thorium loss, right? The loss means the system may not have been in a closed system behavior. Okay, some interaction, some metasomatism, or some metamorphism, or some other magmatic events, some disturbances to the existing rocks could have happened, and in such cases these elements must have volatile, being they are volatile, maybe discarded away from the system automatically due to those processes. Okay, and also some lead loss, intermediate product loss, daughter loss can also happen. Because although we see this 238 forms 207, it's not a direct production, right? It's not a direct production because there are some intermediate steps. Some temporary isotopes are produced during this intermediate production. Because you see here, although we say that 238 produces 206 late, right? In between, there are some other processes. In between, some temporary, short-lived processes are there, right? So in these short-lived processes, if some disturbance happened, you don't get the correct amount of radiogenic accumulation uh, at the measurement. So therefore, your age or your point in the diagram should be maybe discordant. So such reasons can affect the discordance of these samples. And in some situations, if this discordance is systematic, right? Sometimes this discordance is very systematic. And that means they also form a uh, linear pattern. So in that case, there is a possibility to draw a discordia curve. We call it discordia curve, which indicates the behavior of this discordant grains, right? So this discordant grains, when you extrapolate this discordant curve so that it hits the Concordia diagram, you can find out some date from this intersecting point. And here also you have the intersecting point, right? When you extend it, if this discordia is short, like for example, if you have only 3 or 4 points, then your points may be plotted somewhere here. So you make a discordia line, and which is not long enough to hit the curve, concordia curve. So you can extrapolate it so that it will hit the concordia curve, concordia diagram, and then by these hitting points, you can get some dates. See, because this age, this hitting point also corresponds to some age. Say 500 MA. This is 500 MA, maybe, right? Corresponding to that, and this one maybe 4 GA or something, right? 4 GA, not actually in this case 4.6 GA, right? So likewise, you can have two ages. Just just for example, these are not the correct numbers I am referring to. Most of the cases you might get a line like this, a realistic line like this. Let me see, like this. Okay, so you have one point here and you have another point here. So your discordant points are located here, out from the concordia. So in this case, we call this as the lower intercept. We call this as the lower intercept. Lower intercept, and this as the upper intercepts. This as the upper intercept. This we can construct only when systematic edges are found. Systematic distribution is found for discordia points, right? So if you have very systematically distributed points, it means something has happened, some meaningful process has happened. Otherwise, you can't do anything, right? If they are very unsystematic, then you can't do anything. You have to assume that the system has not been closed. Okay, but if these points are very systematic, then you know that some other process has happened. So the point which hits the lower intercepts gives you the most recent date for that process, for that particular process. For example, our Sri Lankan zircons show some concordant edges as well as discordant distribution like this. So we have constructed a line like this, and it hits the Concordia curve around 550. So what does it mean? It corresponds to the metamorphic age of our rocks. So that means the metamorphism has caused these concordant grains to be discordant. But the metamorphism is a process which has affected all the entire rocks. Therefore, this distribution of these points should be systematic. So that's why we could draw a discordia line. So we call it discordia line, right? So from the lower intercept, you get the latest event that caused this discordance, right? So in this case, the 550 MA metamorphism has caused this discordance. So that can be determined by the lower intercept. The upper intercept indicates the age of crystallization of that material, right? Usually this uranium lead dating, we use zircons, right? So in the zircons, if we get the concordant ages for zircon, we say that this is the exact age of magmatic crystallization of these zircons. But if you are getting a discordant age like this, then from the lower intercept, we call this is the time of the last thermal event. That means the metamorphism. And the upper intercept gives the original age of the crystallization of that particular zircon. So that means that zircon was originally crystallized at this stage and later suffered metamorphism at 550 mV, right? So that's why these two ratios have gone down. That means some loss has happened. So this will reduce, and this will also reduce. So in that case, the distribution is like this: reduce, reduce. Okay, so overall what happens is you get some reduction like that. So that's why the concordia point moves to a discordant position like this. Okay, here that has happened because of that. It's just the movement of the I mean due to the loss of those elements, right? So these concordia diagrams are important in uranium lead isotope systematics, but they are very useful because if you have concordant ages, then concordant samples, then you can directly determine its age by this reference diagram. Otherwise, if you have a systematic distribution for discordia, then you can find out two extra events also. I mean, crystallization event of the zircon as well as the later disturbance or the later metamorphism or other thermal event. The age of that thermal event can also be determined from the lower intercept. Okay, so any question until this? You have any question? No, but you have to go through very carefully this section because this is a new isotopic system which is different from samarium neodymium. Okay, right. So this is how we use concordia diagram for age determination of our samples. Usually, people use accessory minerals for this purpose. Accessory minerals means minerals like zircon, zircon and monazite, uh, accessory minerals. So one advantage of these concordia diagrams against the isochron diagrams is, you remember the isochron diagrams we use for rubidium strontium or samarium neodymium? Those systems utilize only one isotopic system, right? Neodymium and samarium in this case, right? Only one isotopic systematics. I mean, the system is one because samarium decays into neodymium. That's all, which is in the case of rubidium strontium, rubidium decays into strontium. But in this concordia diagram, we have two axes. In those two axes, you can remember we use two isotopic systematics, two separate isotopic systematics, right? 206, 238, and 207, 235. So these are two different isotopic systematics we use in combination to get the age. So that age should be very reliable. So that's why zircon ages are considered as very reliable compared to other types of ages, because in combination we use two isotopic two isotopic systematics and get the final age. So it is very reliable. That's an advantage you have in concordia diagrams. So this is an example of Concordia diagram, and you can see these points 1, 2 and 3, they exactly plot on the Concordia curve. So that means all these 3 points are concordant. So we call it 3 separate concordant edges. That means 3 separate edges, I mean 3 separate samples may be uh, represented by here, right? So if you have multiple analysis on the same sample, you will see some clustering. You will see some clustering around this edge, right? If they are like 2 giga years old, right? Here it is 2, and here 2.8, here 3.2, like that. So similar aged samples will cluster at one place, right? So just the interpolation you have to use, because you have graduations here 2.4, 2.6, 2.8, and they are exponential also, right? So you see the distance between 2 points is small here, but the distance between 2 points is bigger here. That is exponential type of variation, right? But still you can interpolate. So we have to interpolate to get the age. For example, age number 2, it's the point is here, right? 2.8 is here, 2.6 is here. So 2.7 may be somewhere here, and your sample is like 2.74 in this case, right? See, like that you can interpolate this age. Number 3 is in between 2 to 2 to 2.2, right? Its age is 2.1. So like that, you can interpolate this one, and since we are using a software or Excel based program, you get the exact value of this interpolation. So therefore, it's very precise. Okay. And also uncertainty can be given by the program itself, plus or minus value, right? Plus or minus value, because all the points might not be 100% concordant. They may be slightly, very little away from the concordia. Maybe in that case 1% error or 2% error. That means 2 million years error, uncertainty or something like that, right? So that is still there. Uncertainty is also there. So therefore, we can use accordingly the isotopic systematics, these isotopic systematics to determine uh, the age of an unknown sample. Okay, right. Another example, but here you see the points are away from the concordia, right? The points are away from the concordia. That means they are discordant, right? Still, you may be able to find out the age of this corresponding age, but since they are deviating away from the concordia, it's very difficult to find out manually. You can't find out it manually. You have to use a software for that. There are geochronology softwares, and also Excel based software, Excel based macros are there. For example, Isoplot. Isoplot is a program which can be used with Excel, that gives you all these types of edges, right? Even discordant edges, even though this sample plots away from the concordia, it doesn't mean that you cannot interpret its age, right? It's possible. It's close to this 2 point something, but you have to determine it precisely. Okay, that is done by the software, right? Some complicated programming is there, so you can have such ages. And also, since they represent a systematic behavior, you can draw a discordia line. You can draw a discordia line and get an lower intercept as well as upper intercept, right? So lower intercept may be giving you some metamorphic ages, the age of metamorphism of these 3 points, right? The 3 points may have suffered metamorphism, and that's why they are deviating away from the this concordia diagram, right? So you get the metamorphic age from here, and you get the crystallization age of this zircon from here, right? Crystallization age means the real age of that zircon grain when it was produced. Okay, right. So this is how we apply concordia diagrams. So as I said, we use accessory phases for this uranium lead dating. Accessory phases means like zircon, monazite, uh, like uh, accessory phases, because they contain a lot of uranium and thorium, right? They contain a lot of uranium and thorium. Therefore, they are suitable for UPB dating, uranium lead dating. But minerals like feldspar or quartz like minerals, even amphibole, they might not be appropriate because they do not contain enough amounts of uranium thorium. Still, they contain some amounts of uranium and thorium, but the amounts are not sufficient so that you don't get a reliable determination. So maybe the error or the uncertainty is very large because detecting very low concentrations are very difficult for some, I mean, in mass spectrometry, right? Very low concentrations will give you very high errors. When the concentration is low, you get high errors, right? When the concentration is high, you get less or small errors, right? So therefore, this is a useful way to use accessory phases like zircon or monazite, right? Mostly zircon is used because they readily make available their crystal lattices for uranium and thorium. Okay, uranium and thorium, because they have large ionic radius and lower charges compared to zirconium. Uh, I mean, lead cannot be accommodated in zircon, but uranium and thorium should be there, will be there, right? So once you have uranium and thorium in considerable quantities in zircon, with time, what happens? They decay into radiogenic lead. So then those newly produced radiogenic lead will be accumulated within the zircon. Uh, since initially they did not contain lead, because lead is a little bit bigger in ionic size, therefore during the crystallization of zircon, normally lead is not incorporated into its structure, but there may be little amount of lead incorporated, which we call initial lead, but it doesn't matter. It doesn't matter, right? But the radiogenic production after radiogenic decay of these existing uranium and thorium will accompany some lead inside the zircon, right? Not the original lead. I mean, the majority of lead is the radiogenically produced lead. So therefore, we consider it as a good for geochronology, right? So since initially we don't have large amount of lead in zircon, uh, you have high uranium lead ratios, because you see uranium is much high in zircon, but lead is very little. So when you divide uranium from lead, you will get a high value, right? High value, right? For thorium is also same. So that makes good geochronometer, right? For uranium lead system, right? For a good chronometer, you must have high uranium lead ratios or thorium lead ratios. That, in other words, indicate initial amount of incorporation of lead, which is non-radiogenic, right? Because if you have non-radiogenic component in large quantities, that will make a problem. I think you understand that, right? So you look at the equation, it's very preliminary and very fundamental. See, so what is our measured value? For example, measured lead equals initial isotopic composition plus the radiogenic production. But when you have very large initial component, then you don't get, I mean, it will make some disturbance to the system, right? Even for producing new isotopic production of lead is impeded by this high concentration, right? It's like another equations තියෙන equilibrium equations අපි අර දෙපැත්තකට අඳින්නේ ඒ වගේ වැඩක්, right? මේක අපි හිතමු xy කියලා XY කියලා එකක් තියෙනකොට මේ දෙක මෙහෙම වෙනවා නම් ඔරිජිනල් සිස්ටම් එකේ Y ගොඩාක් තිබ්බොත් එහෙම මේ ඉක්වේෂන් එක යන්නේ මේ පැත්තටනේ. x y වලට හැරෙනවට වඩා y x වලට හැරෙන තමයි මේ මේක තියෙන්නේ නේද? ඩිරෙක්ෂන් එක කියන්නේ. මොකද y ගොඩාක් ඉනිෂියලි තියෙන හින්දා. අන්න එහෙම වුණොත් මේ ඉක්වේෂන් එක favorable නෑ. So therefore that's why we want as much as possible the initial component less. So that requirement is met by zircon. That's why we use zircon as the geochronometer. Okay, so very little lead is required at the initial time. Right. And this Concordia and Discordia lines, if you see here, you can see this Discordia line normally happens due to lead loss. Okay, normally due to lead loss this happens, because lead loss means some component is lost from here as well as here. Sorry. Right, so some amount of lead is lost, right? This can be due to metamorphism, or because metamorphism is high temperature, it's increasing temperature conditions or increasing pressure conditions, so these affect the crystal structures. So therefore some leaking or some loss of this lead can be there. So in that case, instead of being concordant, they will go for discordant situation, right? So these lead loss patterns are characterized by metamorphic processes. If no metamorphism is there in a terrain, even a later magmatic intrusion, which increases the temperature of the overlying or the already available rocks, can cause this type of discordance, right? But still, discordance is okay, because we can take the lower intercept edge, and we can take the upper intercept edge also. And in some situations, lead loss is a very common thing, but some uranium gain can also happen due to this one. Some due to some processes, right? But those are very rare situations. But most probably lead loss mechanisms are the dominant ways. Uranium gain can be due to some metasomatism or something, right? Because uranium is incompatible, so only possibility to come or to enrich uranium is to supply it from a fluid, right? So that means it's a metasomatism activity, right? But those are not common everywhere. Only for some limited localities you might have uranium gain. At the same time, some uranium loss, uh, if happened in the system, you will get your samples plotted on top of the, outside the above region, this region, above region of the Concordia, right? Normally discordance happens below the Concordia, right? Like here. But there can be some situations where some of your points might be plotting somewhere here. So that means uranium loss, right? Not lead loss, uranium loss. That causes a lot of lead to be accumulated. If you lose the uranium, what happens is you will increase this ratio, right? You will increase this ratio. So therefore, your point will be shifted outside the Concordia diagram, away from it. So that can happen, right? That is also a discordance situation, but commonly happening is this type of normal discordances. Okay. Right. When you date a metamorphic rock, you will see definitely one set of zircons plotting here and one set of zircons plotting here, right? So that, here also you have some zircons plotted, so that you can make a line to find out the lower intercept and upper intercept, right? They will give you two different ages. Okay, so you have another example where discordance, some systematic plotting of zircons, but they plot outside the Concordia. So this might indicate some event which has taken place along this line. So most probably this beta age should represent some metamorphism or some magnetic activity happened during the evolution of these samples. Always remember, for Concordia diagrams, we have these two ratios. Unlike isochron diagrams of isochron diagrams of rubidium, strontium, or samarium, neodymium system. Okay? Why we get this Concordia diagram is because we use two isotopic systems instead of one, right? Two isotopic systems we use so that we do not get a line, a straight line like an isochron in this system. If you want to make an isochron, then you have to go for other ratios. I mean, other ratios means your original ratios for used for the equation, derivation of the equation. Let me show you. Yeah. If you want to make an isochron diagram, then you have to go with these ratios, right? Not uranium thorium ratios, right? These ratios. So they will produce like isochrons you produce like this. Okay. So these ages, this can also be done. People do also some situations, but the Concordia diagram is the most popular diagram to date in the uranium lead system. Okay. So it's a fitted straight line, right? We have to fit the straight line for making the discordia line, right? If you have a systematic behavior only, you can make a discordia line, right? So lead loss event like events can cause this discordia line, as I explained before. Some analysis which you use monocyte might give some points above the Concordia line. As I said before, some points might be plotting here, right? That is possible, especially when you deal with some monocytes, not zircons, but in zircons very rarely you see. But that is also one situation you might encounter due to uranium loss, right? We talked about possibilities, remember? See, uranium loss can cause to plot above the Concordia, right? If you have a uranium gain, then you will have plotted here inside the Concordia like lead loss, similarly. Okay, so I will show you some examples. I'll show you some examples which indicates some ratios of these Concordia diagrams. Okay, so the same type of Concordia diagram, 207, 235, 206, 238. Right here, this is the Concordia diagram, and you can see the age points. This is plotted by isoplot program. So your sample data. So I said if you have multiple samples or multiple zircons, then you might have some clusters instead of one single point. So they are represented as ellipsoids here, right? So when you have many clustering around the Concordia, the program automatically draws an ellipse like this, right? That is also a method in the program. So you have some clear concordant edges because they are plotting on the Concordia curve. So therefore, you can directly have a age for this sample, right? So since this sample, for example, this blue one shows a distribution of ages, you can take a mean age also, right? You can take a mean age for this each ellipsoid, right? So some age like here, you can take as the mean age. This is also possible. And you can see some discordant points here, right? These ones are discordant. They are plotting outside the concordia. They are plotting somewhere inside the concordia, not on the concordia, right? So you can make a discordia line here, right? Some discordia line you can make, the program can make, some options are there. You have to click those options and then it will generate a discordia line also, so that you get a lower intercept somewhere here and upper intercept somewhere here, right? So that means this set of samples, this light blue set of samples have been suffered by heavily some metamorphism or something, right? That's why they become discordant, right? So here you can see some of the ellipses plotting outside of the concordia. They may have suffered some uranium loss or something, right? That's why they are going outside, right? Otherwise they should plot along the concordia. Another example. Yeah, I think the same example, but you see, as you see first, it's very hard to interpret about this discordia line because it's very close to the concordia also, right? But the program can make it enlarged, right? The program can make it enlarged and give you clear discordance line like this, right? So you have two clear edges as the upper intercept and lower intercept, right? The program can do that, right? So that's why we have to use some software to deal with these uranium lead data. Okay, so we have some alternative types of diagrams also, but which are not very useful for you. We call Terra-Wasserberg diagram. This is out of the syllabus content. I don't want to incorporate this into the syllabus, but just for your information, because when you read some papers, you might encounter this type of diagrams. So you see the ratios used. We have used other ratios and come up with the Concordia-like diagram, but in this way, right? The Concordia is this one. This is Concordia, right? But this is another Concordia, but we call it Terra-Wasserberg diagram, right? Because this was discovered by these two people, right? These two people. And this is the typical Concordia diagram. We will focus on this Concordia diagram rather than using this diagram, right? So this is also used in geology, right? Okay, so this is all about the uranium lead system. If you have any question, you can ask me. Uh, but you have to remember the convenience of using uranium lead system, because we are dealing with two types of what two types of isotopic system to get the age. So that means that age should be very reliable, right? Because you are determining in two paths and coming up to one final conclusion, right? Rather than in samarium, neodymium, or rubidium, strontium, even lutetium, hafnium systematics, we use only one equation and one decay scheme. But in lead, we use at least two decay schemes. In the case of Concordia, we have two decay schemes. Or otherwise, if we are using just the simple equations, we have three equations, three systems. Even thorium is there, right? So therefore, it's very, very robust and very useful. Okay. So this is how we apply the uranium lead system. And remember, zircon is the main main accessory mineral used in this uranium lead system. Okay, right. So I want to show you some more some of the more some more diagrams which gives you some implication on some applications. Let me check. Okay, let me show you this one publication. Okay, I hope you can see this document, right? This is from one. Where is it? One complex. Yeah, this is from one complex. Some rocks here. You see Vanni and Kadugana complexes, and petrology, geochronology, geochemistry. Everything has been done in this paper. So let's move to the geochronology part. Okay, so these are the zircons that we have used for age determination. Okay, so is it clearly? Can you see clearly this diagram?
Yes.
You can see different spots, right? These spots indicate the analytical points of for laser. This has applied laser beams. We call it laser ICP, ICP mass spectrometry. Okay, so you have you can see some zircon zonation, right? So this zircon crystallized originally and then later metamorphosed, right? So that means some lead loss event has happened for this zircon. Okay, so original zircon grain you can see here, and you can see a rim. So this rim indicates new metamorphic growth. So lead loss can happen from core to rim, from this core region to rim. So this is how lead loss patterns come into the Concordia diagram. Okay, so these are some examples. So you see some ages are, I mean, some you see here 911 MA, and here 875 MA. So another event has happened at 875, so that has caused this core to grow. So it is not a metamorphic event, because we know only the metamorphism is like 550 mA in Sri Lanka, but so this should be some other magmatic event, some maybe magma intrusion into the existing rock, and the rock which contained already zircon have regrown. So then the lead loss can happen from core to the newly formed region. So then you will end up with the Discordia pattern in the Concordia diagram. Okay, so these are some examples you can see in this type of rocks. For this grain is very clear. At 703, it has formed and crystallized and later metamorphosed. It has suffered metamorphism later. So that's why this rim has been formed. So this rim is 518, the age of that rim. So lead loss must have happened. So if you plot this the age data, isotope data from this zircon grain in the Concordia diagram, you will clearly see a discordant pattern where upper intercept you will see around 700 MA and lower intercept around 518 or something, right? So this is how these grains are happening. Suffered these different metamorphism, and it is reflected in their ages. So this is the Concordia diagram. So you can see the Concordia diagram. Part of the Concordia diagram is only shown here, because the entire Concordia diagram, if you want to show from 0 to 5.5, all these points will be in a very tiny place, right? You remember, because the graduation is very long. But just to magnify, we have taken only part of the Concordia, which is from 500 to 740 segment, right, in the Concordia diagram, right? So our rocks, our zircon grains are plotting in as a cluster in this region, right? It is not necessary always, to show the entire Concordia diagram. You can just show like this for more clarity. Okay, so you see from these clusters you can get a mean age. So we call it weighted mean age. It's like 565 MA. And here you have two types. I think these are two sets of zircons, red and blue. That's why they have shown in two ways. And you see here, these are very almost very concordant. I mean, on the Concordia diagram, you can take as the mean age. But these blue ones are plotting away from the Concordia much, right? So this is the discordance line given by the software. This dotted green line gives you the Concordia Discordia line. So it can give you upper intercept age and also lower intercept age, which is not shown in this diagram, but the program gives you a lower intercept age. See, only the upper intercept age is shown here, because the lower intercept age may be not used in this paper, right? So here also the similar type of Discordia lines you can see given. And see, only in this case you have given both the intercepts, upper intercept and lower intercept. So upper intercept is 958 somewhere here, and lower intercept is 543. These are the Discordia ages. Okay, so here also you can see the upper intercept and lower intercept ages are given. So the upper intercept always shows the original crystallization age, and the lower intercept gives the latest lead loss event, right? It may be a metamorphism, or it may be another magma intrusion or magma mixing or reaction or whatever, right? It depends on the situation. So once we get this data, you can make a histogram also with these ages and find out which is the dominant age. Okay, so here you can see the dominant age is around 570, right? In this population, it gives a dominant age at 570, and also the upper intercept ages and also the crystallization ages of all zircons will give you some other dominance here, which is above 800 MA, right? See here. So like that, you can make some histograms also in this for discussion of different age groups in these rocks. Okay, so these are how these zircon ages are interpreted. Okay, right. So if I just show you some interpretations, you see some subduction at the very old ages, maybe 800 or 700, and later collision making the metamorphism, right? So this is the metamorphism, and which formed the one in Highland complex. And see, some magma can be generated, new magma. So this new magma can produce new zircons, right? And also the metamorphism can produce new zircons. So in the Concordia diagram, at young ages, you will see this the zircons produced from these magmas and metamorphism giving younger ages, whereas the old ages are given by the zircons which contained in these older rocks, right? So that's why we get some age population in different rocks. Okay, so this is a kind of an application, and one more thing I want to show you. Do you see a slide containing the mantle reservoirs, title called mantle reservoirs? No? What about now? Do you see this new slide?
Yes, sir.
Okay, right. So I just want to show you some application, another application, which we call some combined isotopes to use trace element or what is as I mean isotopes as a tracer for different processes in the Earth's interior. So we at the beginning we told that we are using isotopes not only for age determination but also for tracing different processes, right? So this is one application in such situation. So here we have applied neodymium and strontium isotope ratios in a combined diagram. Actually, this shows the mantle reservoirs. I mean, this is uh, showing some the isotopic ratios as applied to mantle reservoirs. So there are several mantle reservoirs. One is depleted mantle. You remember depleted mantle, and the other one is bulk silicate earth. So that also you can remember, right? We talked about these things before. Depleted mantle, bulk silicate earth, and also there is some another component called EM1, EM1 and EM2, two components, another two components, and there is another one called high mu, high mu, high mu. This is another mantle component, and the average mantle composition is given by prema. This is called prema, or in other words, you can call it prevalent mantle composition. Okay, so likewise, there are several mantle reservoirs. Okay, these are the main reservoirs that I just mentioned. Okay, so so these mantle reservoirs indicate some fixed type of compositions. So if you have a rock, your rock plotting your isotope signature somewhere here, right? Somewhere here, which is linearly or systematically distributed like this, then you can consider it's a mixture of depleted mantle and one of the components, maybe EM1 or maybe EM2 or something like that, right? Because if you have one component here and another component here, uh, your composition should be lying in between these two. So in this case, we call two component mixing, right? So your sample might have suffered some mixing process uh, with equivalent compositions from this component 1 and component 2. Some situations your sample might be plotting somewhere here. One set of samples are plotting in this way linearly, and another set of samples are deviating from that line and plotting somewhere here. So in that case, you can consider another component is affected there, right? So another component might have affected, so that means it may be affected by three components. So in this case, we consider three component mixing, some mixing from here, some mixing from here, and some mixing from there, so that your sample deviates towards this direction, right? So likewise, we can analyze our trace elements or rare earth elements and isotopes. uh, yeah, this can be applied for rare earth elements and trace elements also, right? But here we apply it with isotopes. Okay, to understand the past history, what kind of geochemical processes have made this type of distributions. Okay, so we will just see some of those distributions. And these reservoirs, mantle reservoirs, if you are important in this explanation of these mixing behaviors. Okay, so in this type of situations, we cannot apply direct isotopic systematics to determine the date. Why? Can anybody explain it? Even though you measure isotope signatures, you can't use them to determine the age. Why is that? We have already discussed this in principle. Can anybody think? We had some assumptions. Remember, the systematics should be, the isotope system should be closed system. Okay, then only we can apply the age equation. If the system is not what you call, not in a what closed system, all these assumptions will be invalid, and therefore you can't subtract measured value minus initial value equals e lambda t something. That cannot be applied, right? So mixing means it is affected, right? It's not the system closed. One component has come into another component. That means they are open system. But still, the isotope systematics can be used to trace those mixing procedures, mixing processes, rather than doing age determination, right? Age determination is not possible. But still, remember, uh, zircon, being a very robust mineral, does not get affected by this any mixing or anything, right? Any type of these processes. So therefore, uranium lead system might be suitable in zircon to apply for age determination, even for a mixing affected rock. But samarium neodymium or rubidium strontium systematics cannot be used. Remember that, right? Because in zircon case, we are taking the isotope systematics within the zircon crystal itself. So being zircon is a very robust crystal, it does not allow anything to come into its structure or going out from its structure, right? Even lead loss thing happens within the grain itself, right? From one zone to another zone, right? Not from the zircon to another outside, right? So therefore, uranium lead system is good for that, right? So that is another advantage of uranium lead isotopic systematics for age dating. Even for a geochemically affected rock, you can use zircon uranium lead dating for age determination. Okay, so anyway, we can use these isotopic systematics to understand geochemical behavior of our intended rocks. So since they have specific regions in terms of these strontium neodymium diagrams, right? Whatever the isotopic systematics, you can have some fixed region for different n members. For example, depleted mantle. So if the depleted mantle, if any rock is coming from upper mantle melting without affecting any secondary process, that should plot within this region. Okay, that should plot within this region uh, if any upper mantle rock is there which has not been affected by any process, right? But some rocks are affected, even upper mantle rocks, some are affected. For example, this EPR is not a mantle reservoir, it's a location. Okay, it's called East Pacific Rise. It's a mid-ocean ridge, one of the mid-ocean ridges. And this one MAR means Mid-Atlantic Ridge, right? Uh, these rocks typically show some affected features. That means they are really coming from depleted mantle because they are MOB, mid-ocean ridge basalts, right? You remember I told mid-ocean ridge basalts are products of depleted mantle. Then they should inherit the depleted mantle isotopic composition. But uh, in situations, in some situations like here, shown here, you can see these mid-ocean ridge basalts are plotting some deviated from its typical expected composition. They are deviating towards downwards. Okay, so that means they are affected by uh, any other component, maybe high mu, or maybe EM, because EM can also affect, right? This can affect like this. EM1, EM2, they can affect. So that original composition goes in a direction like that second component towards a second component direction. Okay, so these type of situations are there, so which we can use in modeling, geochemical modeling, and also we can determine direct isotopic composition of our sample and plot them in a standard diagram like this with these mental reservoirs, so that we will be able to find out what kind of a component has affected its composition, right? In some cases it may have affected very severely from EM1 or EM2 or something. So in that case, your sample might be plotting somewhere here, although it's a mid-ocean ridge basalt. So that means your original mid-ocean ridge basalt has been affected by a melt derived from this EM1, right? Enriched mantle. EM1 means enriched mantle. There are two zones for enriched mantle. That means a typical mantle is here. Okay, typical mantle is here, that is depleted mantle. But some places are there in the mantle which shows very different composition than the average composition, right? So such two zones are there, which is called EM1 and EM2. Okay, so this is another process actually. Subduction slabs bring many materials and enrich the mantle, and then this mantle become very different from its typical mantle composition, right? So likewise, different zones may have created within the mantle itself, right? So this is how the different mantle reservoirs are generated. Okay, so anyway, we can use these diagrams, standard diagrams, to show these interactions. Okay, right. So in different isotopic systems, you have these different different characteristics, right? So the first mantle reservoir that we considered was is to bulk silicate earth, that you already know, which is the original silicate composition. So normally we remember we considered the bulk silicate earth composition is still preserved in the lower mantle region, right? Because the upper mantle has already started melt extraction, or the melting, which has extracted the continental crust and then derived the depleted mantle, and like that a lot of melting is taking place and modifications are there. But in the lower mantle region, very limited modifications are there. So therefore it already contains original composition, right? Original composition means bulk silicate earth composition, original composition, so which is very close to the composition of the lower mantle, right? So you can consider bulk silicate earth approximates the lower mantle composition. So this is one of the reservoirs, mantle reservoirs. The other one is a depleted mantle, which is the upper part of the mantle. We have already discussed the uppermost part of the mantle, the depleted part, depleted mob mantle, which forms the mob basalts, right? So you can remember the neodymium difference, strontium difference, isotopic difference, right? Neodymium is high in those parts because it is depleted, and strontium is low, right, in depleted mantle, right? We discussed about these things in when we did isotopes for those two systematics, incompatibility and compatibility. Remember, all this matters. Okay, and then we have the EM1 enriched mantle. It's type 1, we call it EM1. And you can see the difference in EM1 is it has lower strontium isotope ratios than EM2, right? Strontium, because the EM2 is supposed to have higher strontium further going there, but EM1 having isotopic composition somewhere here, and which is very close to the primordial isotopic composition. What is the primordial isotopic composition? Primordial isotopic composition means bulk silicate earth isotopic composition. Soon after core formation, we had the silicate portion of the earth after core separated, right? So it is almost close to the primordial. That means the initial time at the time of earth's formation. Another term for that, primordial composition, right? So its strontium isotopic composition is almost primordial. See, it's almost primordial, same as strontium, I mean BSC, but the neodymium composition is much lower than the primordial composition. Okay. So this is another reservoir, the EM1, and we have the EM2 also, which has relatively higher strontium isotopes than the EM2, sorry, EM1, and also it is different from the primordial composition also, right? EM1 has primordial strontium, but EM2 does not, right? It does not have the primordial, it's different. It's extremely enriched. But in the case of neodymium, EM2 also plots somewhere here, okay? Strontium is high, but neodymium is almost same, right? Neodymium is almost same. Since this is out of the diagram, I can't show you the exact place, but just keep in mind that neodymium is almost same, right? So almost similar neodymium ratios are there, but strontium is different. That's how you distinguish those two mantle reservoirs. And then what we call the prevalent mantle, prema, it's kind of a restricted portion. It's kind of an the average composition of the mantle, because you see depleted mantle is here, enriched mantle is here, so an average is given somewhere here, like that is what you call the prevalent mantle. Okay, so this is just an enlargement of the same diagram, and so you can see these diagrams very, I mean, so many samples are plotted. This is you see East Pacific rise, mid-Atlantic side, and several other places. I think somewhere this should be mentioned. Yeah, see, different places, different regions of the earth, right? Galapagos, Hawaii, many places, right? So all these places show, for example, Hawaii here, right? They are almost in between the enriched composition here and the depleted composition. So they represent more or less two member or two n member compositions, two n member effects, right? 50-50, like 50 from depleted mantle, 50 from enriched mantle, like. Okay, so likewise, if we have some samples measured and our samples plot somewhere here, then we can decide that our samples may have affected by two of the n members from here and from here. Okay, or otherwise it might have been affected by three n members, like this: depleted mantle, enriched mantle 1 and enriched mantle 2, so that it is coming around here, right? These possibilities are there, but actually to determine which is the correct scenario, we have to model. So that is what we call the isotopic modeling or geochemical modeling. We take these n members and we do some calculations, triangular calculations, so that to find what are the best components, or what are the best contributions from each of these components: 20% from EM1, 10% from EM2, 40% from DM, like that, right? That can be determined by geochemical modeling, which we don't go to do at this stage. Okay, so this is the application of isotope systematics for mantle reservoirs. Okay, so so far I have shown you neodymium and strontium applications, but you can extend this to lead isotopes also, right? For lead isotopes also you can extend this one, uh, so that you can make some modeling, right, in the future. Right. Always remember this depletion and enriched pattern, enrichment pattern, depletion and enrichment pattern gives you crust mantle array. So we call it crust mantle array because enrichment is always associated with the crust and depletion is always associated with the mantle. Right. So therefore we call this distribution as the crust mantle array. Crust mantle array. Okay. Right. So anyway, this is how we do this isotopic systematics uh, for n member composition determinations. N member composition determinations. In lead isotopes also you can have the similar diagrams in uh, uh, for n member compositions. So you see here, this is a lead isotope diagram showing the n member composition. So EM comes here, EM1 and EM2, and depleted mantle here, prevalent mantle here, uh, and high mu is here, like that. Actually, this high mu means uh, there is a term as mu for lead isotopes, right? They give you some uranium lead ratio, which is high. Therefore, it's called high mu, right? So, which we are not going to discuss in detail, right? That is how the name has come there, right? So, most of the samples in the global samples are can be explained by these three n member compositions. In lead isotopes, it's very clear: depleted mantle, enriched mantle, and high mu, right? Either like that or like, sorry, like this, right? Some triangular plots can be generated and explain their mixing behaviors. So these are applications, isotopic applications, which we don't discuss in detail at this level, but just keep in mind that these isotopes give you some possibility for tracing geochemical processes, right? Not only age dating, right? So this is just the normal ratios of isotopes, not the Concordia, not the isotope ratios that were used for Concordia, right? Remember, these are the ones that we use for the normal equation, age equations, right? But here we are using that for to understand the mixing behaviors, okay, not for age determination. So this is how we apply the isotopic systematics. And one more, just one more thing that I want to show you. There is something called geochrome. Okay, there is something called geochrome. This is applied in lead isotopes only. Okay, this is used in lead isotopes only. And this geochrome means the isochrone, because in the lead isotope age determination equation we use these two ratios. So therefore, if you plot and if you find a line, then you can call it isochrone. Okay, like in the samarium neodymium system and rubidium strontium system, we had some isochrones, remember, that can be used for age determination, right? So likewise in the lead isotopes also you can use this if you want to make age determination. So the all the chondritic values or the chondrite ratios, bulk silicate earth values, all plot in a single line like this. So this is what we call the geochrone. Geochrone means the age of the earth is reflected by this isochrone. This is 4.5 billion years geochrone, right? So that is also shown in most of the lead isotope figures just as a reference line. Okay, so this is an isochrone given by meteoritic samples, which gives the age of the earth, right? So now you can see most of our rocks, the existing rocks from different areas, plots to the right of this isochrone. Okay, plots away from this isochrone. So this is another problem also actually, because that problem I am not going to discuss because it's called a paradox, right? It's called a lead isotope paradox because there are no reservoirs except for this EM1, very little, I mean not enough in mass, uh, because the samples in the world should plot in both side of this geochrone, because this is the isochrone of the planet Earth, but most of our samples are plotting right side of the isochrone. So this is a problem, right? It's a geochemical problem actually, unexplained yet, which we call the lead isotope paradox, right? You just search in the Google what does it mean, okay? But you don't need to take it for your syllabus because it is out from the syllabus. But just for curiosity, if you want, you can just search and find details, okay? And this NHRL means Northern Hemisphere Reference Line, because most of the rocks in the Northern Hemisphere are plotted along this line, most of the rocks. So that's why actually you have this, most of these rocks are plotting along this line, although they are showing a cluster, right? That's why it's called Northern Hemisphere Reference Line, and it is reflected in lead isotopes only, not in samarium, neodymium, or rubidium, strontium, or anything, right? It's a special line that is constructed in lead isotope diagrams. So normally in lead isotope diagrams, you can see geochrone and NHRL. These two diagrams are there just for our reference, right? So this is how we apply the isotopic systematics globally to understand geochemical processes, okay? Apart from age dating. Okay, so this is what I wanted to teach you under the Isotope Geology last lecture. Sorry that it exceeded 2 hours, 2.5 hours almost. So I think this is what we have to cover under the syllabus. So those who want to pursue for higher education in petrology or geochemistry, you must learn more, but not now. Later you can read more the other sources and learn, because when we encounter a lot of master or PhD graduates in from other countries, right? They are in geochemistry. They are, I mean, ahead of us, right? We have experienced it already. So that means we are lacking some modeling part or some applications in our fundamental courses at the undergraduate levels, right? But I advise you, but of course there is no time also for going for extended discussions. That is another reason, unlike in our times, not our times, previous times, where all the examinations were done at the end of the years. We had enough time. They had enough time for discussions, longer classes, not like modules, right? Some subjects were there, right? Not just simple modules like what we have now, right? Multiple modules we have, so we have to finish them as soon as possible. So this credit system has made everything busy, so that we have very short time for in-depth learning, unless you do self-learning. Okay, right. Anyway, so this is what we have to discuss today. And with this, I finish the Isotope Geology lecture series. And I hope you gathered some knowledge, and please make sure that you you clearly get the points understood. And if you have some questions, you can ask now, or even you can send any email or anything if you have something unclear. Okay, do you have any questions now? And also I told you the three books, you must read those three books. I mean, no, not all the content, but the places where you find the relevant information relevant to our lectures. Okay, do you have any questions? This is the so I would like to finish the session then, if you don't have questions. So this is the end of our Isotope Geology lecture series. I hope Professor Pitawala has completed the stable isotope section. So both sections will have in questions in your end semester examination. Okay, right. Good luck.